Hello again. This is Math 1115 Alternative Delivery for April 8th, and the content covered is sections 5.3 and 5.4. Please be active learners using this kind of a button to make sure that you're learning and having pencil and paper. And I encourage you to make some of your own magic today. Stay the course. There is magic in fighting battles beyond endurance, and you're not alone in doing this. Also, teaching and learning is continuing unabated. Grades will be earned and rendered, and your educational goals need not be deferred. Stay the course. That's what champions do. The first topic today is going to be solving systems of two linear equations and two unknowns algebraically. We've done this by doing a graphical method where we could kind of approximate the answers, and you can use a calculator to get close to being the right answers, better accuracy than you can guess. But these both techniques that we're discussing today, all three techniques actually we're discussing today, give exact answers. And I will be testing you on these as well as being able to find graphical solutions. And so here's the recipe. And the first technique is called solving them by substitution. So you solve one equation for one of the unknowns, substitute this solution into the other equation, and then you have a linear equation in one unknown. You solve the resulting equation for the value of the unknown it contains and substitute back into the equation of step one and solve for the other ones, and then it says that you can check. Now, like most recipes, this is harder to read than it is to follow examples, so I'm following John's suggestion again, and I'm going to take you through some of the examples. So here we go with the first example. Here's the system that we want to solve by substitution. So what we're going to do is we're going to solve for one variable in terms of the other. And if you look up here, you can say, oh, it's probably easy to solve for x. And in fact, it is. X is equal to 3y plus 6. Now I'm going to take that value of x and substitute it into the other equation. And so everywhere I see an x here, I'm putting that 3y plus 6. So I do that. I have one equation and one variable. So I solve that and I find that y is equal to minus 1. But now I can take this y equal minus 1, substitute it into this equation, and find out that x is equal to 3. So we've solved them exactly by substitution. Here's another example, solving by substitution. Now, in this case, it is not as easy to solve for one of the variables. But what we're going to do is we're going to solve for y, and we're going to solve for y in the first equation. So the first step is we would add 5x to both sides, and then we would divide all the way through by 2. So we know that y is equal to 5x minus 4 over 2. Now I take that and I put that into the second equation everywhere I see y. So I will have 10x plus 6, this is where the y goes, is equal to 3. I do some simplification and solving. I found out that x is 3 over 5. Now I will take this 3 over 5 and I'll substitute back into this equation, and it will tell me what y is. So when I substitute that in this way, I get y is minus 1/2. So it is 3 over 5 and minus 1/2. That's by substitution. The next technique that we're going to do is called by addition or subtraction. And in fact, in most courses I teach and books I use, we refer to this as elimination. And so we're going to eliminate a variable by addition or subtraction. Okay, again, the recipe is going to seem much more complicated than actually solving these. But write the equations in the form of 5.4. Now this is what 5.4 is, and this is very important. So you want to have the x's under the x's, the y's under the y's, and the constants under the constants in this order. Then we multiply all terms of each equation by a constant chosen, so the coefficients of one unknown will be numerically the same in both equations, and they can have same or different signs. And sometimes it says you'll add, sometimes you'll subtract. This is actually easier than the directions will make you think. And then you solve the resulting equation for the other unknown and substitute this value back in. Let's look at some examples. Okay, so we want to use the method of addition or subtraction to solve this system of equations that you see here. Now, these are in the form that I wanted them to be, so I didn't have to do any rearranging to get them there. And now what I'm going to do is I'm going to I'm looking at the coefficients, and what I want to do is I want to multiply all the way through by something that, well, actually in this case I guess I can just add the two. So let's just add the two. So draw a line here, and I'll add down. I'll get 3x. These will cancel by design because I observed that those will cancel. This gives me 9. So 3x equals 9, so x is 3. Now if I know x is 3, I can take that x equal 3 and substitute into either one of these equations up here. We're going to substitute into the first one. So x is 3, so it's going to be 3 minus 3y is equal to 6. That tells me y has to be minus 1. So again, what we observed is, we can add them vertically and make that drop out. Now sometimes it's not as easy to do. And the following example indicates subtracting one equation from the other. And they tell you to be very careful with that. Because of cautions like this, I usually recommend students fix it so when they add, they have one variable drop out. And this can be accomplished by multiplying all the way through on both sides by a minus 1 ... or perhaps some other value. So let's look at this, this problem right here. Okay. Now, none of the variables will drop out, although it is in the form that we want it. So that is the good news. But now what I'm noticing is that if I multiply the second equation all the way through by 3, I'll have 3x here and I'll have 3x here, which means I can subtract them. And so down here, what I'm doing is I'm multiplying both sides by 3. So I'm taking 3 times this side and 3 times this side. That gives me 3x plus 9y is equal to 6. But you see, now I force those to be the same. And now what I can do is I can subtract the bottom equation from the top. These will cancel out by design, and I'll have minus 11y is equal to minus 2. And we find that y is 11 over 2. Now I can take this value of 11 over 2 and substitute it into either one of the original equations. We substitute into this one, and we find that x is equal to 16 over 11. So the solutions are 16 over 11 and 2 over 11. Some of my students will say, Jim, those are the ugliest damn numbers I've ever seen in my life, but I tell them there are no ugly numbers, just like there are no ugly babies. Here we're doing something a little bit different to solve the same system of equations. And what we're doing here is we're multiplying the top equation through by 3 and the bottom equation through by 2. And you see what we're doing is we're forcing this to be minus 6 and this to be plus 6. And this is actually the way I probably would remember, because then it's easier to add. Students make less mistakes adding than they do subtracting. So we add, and we get x is equal to 16 over 11, just like we did before. And we can substitute again, and we get y is equal to 2 over 11. Life is a word problem, though, and here's an example of a word problem where we solve that. So by weight, one alloy is 70% copper and 30% zinc. Another alloy is 40% copper, 60% zinc. How many grams of each are required to make 300 grams of an alloy that is 60% copper and 40% zinc? So we let A be the number of grams of the first alloy and B be the number of grams of the second, and so our equations are this. A plus B has to add up to 300, and the final alloy will have 180 grams of copper. That's because you got 60% of the first alloy, 60% of the 300, and 40% of the second. And so 70% of the first plus 40% of the second is equal to 180. And so we get values that look like this. A plus B add up to 300. 70% of A plus 40% of B is 180. Now what we do here is we can multiply each term of the first equation by 4 and multiply each term of the second equation by 10 because we want to move those decimal points. So we get this, then we subtract, the b's will cancel out by design, and we will have, here we're subtracting the first equation from the second, and we get a is 200, and we substitute back in to the first equation, and we get b is equal to 100. Sometimes we have to rearrange things in order to solve a system of equations. For example, this system is not in the form of that we want, where we had the x's and then the y's and then the constants on the other side. So we have to reorganize this into this form before we solve it. But once we do, we can go ahead and solve or try to solve this problem. Now, if we multiply the second equation by 2 and subtract, we get this. This is 0 equals minus 1. Now 0 is never equal to minus 1. That means there is no solution. And you might recall that that means these are parallel lines. That means the system is what we called inconsistent. The lines are parallel. If we had solved and tried to solve this and things dropped out and we got 0 equals 0 or 5 equals 5, something is always true. The system is dependent, and that means there's an unlimited number of solutions. They're really the same line. Okay, let's give a go at this and see how you have mastered this. We're going to do number 6 together. So we want to solve using the method of substitution. So press pause, solve the problem, and then check back. Let's see how you did. You should have gotten x equal 5 and y equal 2. I hope you did. If you didn't, make sure you understand how to do problems like this. Let's do sum by elimination. And here I'm going to ask you to do problem 18. So you're working on problem 18. Please hit pause, do the problem, and we'll see how you did. Let's see how you did. Again, we had to reorganize that because we want the capital R's under the capital R's, the lowercase r's under the lowercase r's, and the constants under the constants. But now what we can do is we can add the equations together. We get 4r is 20, r is 5, and we substitute 5 for r into the first equation, and we find out that r is, lowercase r is minus 3, and uppercase R is 5. And life is the word problem, so we do study word problems. Here we have an underwater, but near the surface, explosion is detected by sonar on a ship 30 seconds before it is heard on the deck. That's because sound travels faster underwater. If sound travels at 5,000 feet per second in water and 1,100 feet per second in air, how far is the ship from the explosion? Okay, you got to think about this, set up the equations, and solve. Please hit pause and solve the problem. Let's see how you did. Now, here distance is equal to rate times time, so we let T1 equal the time for sound to travel through air, and T2 be the time for sound to travel through the water. Okay, so they went the same distance, so distance equals rate times time, or velocity times time. So this distance has to be the same as this distance. But we also know that the time through air was larger by 30 seconds. So that means that we have T1 is equal to T2 plus 30. So we have two equations, this one and this one. Two equations and two unknowns. We're solving this by substitution because we know T1 is equal to this. So we substitute that into this first equation and we solve, and we get T2 is equal to 8.4 seconds and T1 was 38.5 seconds. But the question was asking us how far away was the explosion, so we have to use either one of those values. Distance equals rate times time, and we understand that that explosion was 42,300 feet. Next we move into talking about solving two equations and two unknowns by determinants. So, and they will refer frequently to this this setup, and we need to know this. We're going to be using a technique that is going to be called Cramer's rule. And the reason I'm covering this section is because I do know you do this in electronic technology circuits with Kirchhoff's law and things like that. So we need to have things in the x's over the x's, the y's over the y's, and the constant over the constants before we begin this process. And we're going to solve these using a technique called determinant. So we better talk about what a determinant is. So a second order determinant is, and notice I took, these were the x numbers. These are the y numbers, and I put bars there like an absolute value as a symbol for the determinant. This is going to be a1 times b2, a1 times b2 minus, and then it's going to be b1 times a2. This minus is from the formula, but it is possible for a2 or b1 to also have a minus in them, so be very careful about your signs. And your author thought this was a useful figure for you to remember. This is plus, and this is minus, multiplying that way. So let's evaluate a couple of determinants. So here we have minus 5, 8, 3, 7, and so it's going to be this one times this one, and it's going to be this one times this one, and I'm going to subtract the 2, and I get minus 59. Here are 3 more examples. Here you're going to have 4 times 17 minus 3 times 6, that will give me 50. Here you're going to have 4 times 17, and that's going to be minus 3 times 0, which is just going to be 0, so that is just going to be 68. And down here you're going to have 3.6 times minus 17.2, and it's going to be minus, and notice here's the minus from the formula for determinants, but here's a minus because the 3.2 was minus 3.2 times 6.1. Now here a minus times a minus is going to be a plus, so the net here is going to be minus 42.4. Okay, so having practiced determinants then a little bit, we'll talk about Cramer's rule. Now, once we get it into this form, here's what we're going to do. The denominator in Cramer's rule is going to be the determinant of the coefficients on x and y. So if you look over here, you see this is a1 over a2. This is b1 over b2. That's the denominator both times. And we can only do this if the denominator doesn't equal to 0. Now to find the numerator, what we do is, if we're solving for x, we replace the x coefficients with the constant terms. So I'm replacing the x coefficients with C1 and C2. And this one remains the same. And for solving for y, what I'm going to do is I'm going to replace the B1, B2 by the C1, C2 again. That's what I'm doing. And that's what this says. So, and of course the denominator can't be 0. If the denominator is 0, you have to resort to other techniques. There is not a unique solution, and Cramer's rule cannot be used. Okay, some important features of determinants in Cramer's rule. The determinants in the denominators are the same and are formed by using the coefficients of x and y. In the solution for x, the determinant in the numerator is obtained from the determinant in the denominator by replacing the x coefficients with the constant terms. And similarly, number 3, in the solution for y, the determinant in the numerator is obtained from the determinant in the denominator by replacing the y coefficients with the constant terms. And they say, again, as I've tried to stress, make sure you're in this form before you try to use this. So let's look at a couple of examples, I think. Here is a problem to solve. Now notice that I have 2, 5, 1, minus 2. And my denominator is 2, 5, 1, minus 2. And down here it is 2, 5, 1, minus 2. So you see my denominators are the same. Now my numerator, to solve for the x, I'm going to take the constants, 1 and minus 11, and replace the x coefficients with those. And I'm going to evaluate the determinants. You should do this for practice, and you'll get -1. And to solve for y, what you're going to do is you're going to take 1 and -11, and you're going to replace the y coefficients with 1 and -11. Calculate the determinants, and you'll get 3. So therefore, the solution is -1, 3. And by the way, they make note down here that since the same denominator appears in each numerator, you only need to evaluate it once. So to solve this problem, you have to evaluate 3 determinants. Some students find this much easier than solving it otherwise. Life is a word problem, so let's look at a word problem. You got 2 investments and yield a total income of 700. And the 2 investments totaled 18,000. Okay, so X plus Y add up to 18,000. But the first investment was at 5.5%, and the second one was at 3%, but it netted a total income of 700. So you see you've got 2 equations and 2 unknowns. So what we have is 1, 0.5, and we have 1 over 0.030. And then we use Kramer's rule to find out that X is 6,400 and Y is going to be 11,600 by substituting back into the original equation. Is probably easier than calculating another determinant. Okay, again, they must be in the form before setting it up that way, and this can be determinants can be easier, particularly when the coefficients are decimals. Let's do a couple of problems and see how this worked for you. Here, let's do problem number 24. So hit pause, do problem 24, and then we'll check back. Let's see how you did. In 24. You have to, and by the way, you have to write both equations in standard form. So you got to get the x's over the x's, the y's over y's, and the constants over the constants. This is what you should have gotten for x. And this is what you're going to get for y. There is more, but this concludes the coverage of Chapter 5. Chapters 5 and 6 will be quizzed together, but there's a project in the offing. More on this very soon. Watch your emails. Take care. Oh, actually, I didn't sign off yet. Now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And very importantly in these days, take care of you and yours. Bye for now.